Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh, yeah!
Okay, a little cartoon to start us off here. So the topic for today is vectors. As our little friend from Despicable Me was saying. It has both magnitude and direction. He did not make that up. All right, let's get some examples. Oh, let's talk about driving. If you are going 50 miles per hour north, you have given yourself a vector. If you just say, how fast were you driving? I was just going 50 miles per hour. You didn't give me a vector because there's no direction. That just means a scalar. Magnitude just means how much, okay? There's lots of different categories of vectors and scalars, and we're going to fill in this little chart here. Let's start with velocity. How fast you go. So we always use a V for it. Sometimes you'll see a little arrow on it because of that. We typically only use meters per second. These are going to be units. You can put parentheses on them, or kilometers per hour. Those are our two. If we have to do anything in miles per hour, we will convert. A scalar would be speed. That's how fast you go, but nobody cares which way. We also use a V for it, and we still use meters per second and kilometers per hour. There just wouldn't be any direction. Those kind of have a pair. Okay. D is for displacement. Typically we're doing meters or kilometers. Okay. Distance. Well, distance is also D. It's also meters or kilometers. They're very different though. We'll talk about this when we do east and west. Well, let's do it right now. Okay, let's just say you start at your house. You drive to your friend's house. And then you go back home. And let's say it was 10 miles to your friend's house. Your displacement, because you started at home and came back to home, means you went nowhere because your start point was 0 and your end point was 0. Your distance was 20 miles. This is an odometer reading. Now, these ones are coming up in our next unit, but this is your list for like the whole year. Okay? Acceleration. We use a little letter A, and those are meters per second squared or kilometers per hour squared. Okay, there's no matchings on these, okay? I just have different lists of different things. Time, generally T with a curve on it, and we use seconds or hours. Okay, force, we use a capital F, and our units are generally only newtons. Work or energy, that's supposed to be a slash. They usually use a W. We could use a capital E, and the unit will be joules. I'll just write that one out. And yes, we actually use a capital J. Okay, and the last one for our list here, momentum. It's a lowercase p, but just be careful because over here we're going to have power, and that's a capital P. So make them big. Power is measured in watts, although you probably like horsepower, and momentum is it's short units. It's kilogram meters per second. But that one actually can vary. So now you have your list. This is actually for the whole year. So when we represent a vector, we do just draw an arrow, and we say 20 meters east. Why is it east? Because I drew to the right. And we're going to get to the drawing part of this, okay? It's not to scale, but drawing. There are two conventions or ways that vectors are described. The first one is, I call it the quadrant direction. It's just like in math when you're dealing with angles on a, from 0 to 360, first quadrant, second quadrant, third quadrant, fourth quadrant, all that stuff. Or we have the cardinal direction, which is just using a compass, okay? So this could also be just called the compass direction. Okay, so let's start with the cardinal. Here is a cardinal axis. Well, the cardinal axis goes from 0 to 90 to 180 to 270, and this is technically 360. So for example, everything starts at 0 in the counterclockwise direction. That's why it's also called counterclockwise. So starting from 0 to here, it was 40 degrees. So cardinal, it would be 40. This one's already printed for you. This one started at 0, 90, 180, here's 270, and obviously it went, if it's 240, it went 60 degrees more past the 180. So you have to think of this as 0 to 360. Now I'm going to change colors because we're going to do the quadrant. I need you to label all of this. So to use the compass directions, I'm going to just write on top of this. This is north. I don't know if you can tell the difference. That's blue. Guess it's not blue. What does it got another color? Hold that thought. It does show up better with another color. I'll try red and see if you can see it. This would be east. This would be south. That's an S. And this would be a W. Now, if you think about a spinner on a game, starting at 0, it can spin anywhere. So quadrants are easy. You just go 0 to 360. We actually don't use the quadrants all that often. We actually use north, south, east, and west. So you have to imagine that the spinner can move into this area. Let's make a little arrow. It can spin over to this area. And it actually doesn't matter which one you draw. I'm just drawing on this one. And it can go to this area. So I can have all sorts of angles. So when we're doing compass direction, we're only looking at angles from either the x-axis or the y-axis. And it's not about how big they are, it's about where they are. I'm going to put doubles on the ones that are to the y-axis. If I start from the x-axis, remember this is x, this is negative x, this is y, this is negative y. East is corresponding to positive values. North is corresponding to positive values. West corresponds to negative x values. South corresponds to negative y values. If you're in this section, this angle, whatever it would be, is considered northeast. If I touch the x-axis, it's northeast. Below it would be southeast. This, touching the west axis, would be northwest. It's technically north of west. This would be southwest. When you draw your angles in, again, the compass one starting at north, and you need to all be drawing this, don't just watch, this is actually called east of north, east of south. This would be west of south, and west of north. There are some conventions that make this easy, but there's also a little bit of hard. So we like to use these just because they sound normal. Most of you do too. So as long as we always go X first and we move away from it and rotate it, again, think of like a spinner on a game of life or one of those games, you're going to want to refer to this a lot of times. Okay, so how do we add vectors? So we're going to start with sort of the easy stuff first. Why not? Okay, a plane's going to head west. Well, at a velocity of 200 kilometers per hour, it encounters a tailwind. So what's a tailwind? Here's my plane going west, and a tailwind pushes at the tail. Guess what? They're both west. Now, the drawing method, which we're not doing to scale because we're not all in the same place, but generally speaking, we can at least sketch a picture. When we add vectors, we place them tip to tail. And you'll do a little activity, or at least I'll do a demo that shows you it doesn't matter which one you put first. And the bigger ones, I just use bigger arrows, but I'm going to use my directions, north, south, east, and west. So I have a west plane at 200, and I have a tailwind at 40. They kind of touch. This one's 40. What is the resultant velocity? Well, there's no angles here. It simply adds together because they're in the same direction. So it's going to be 240 kilometers per hour, keep track of the unit, west. They add it together. If they're in the same direction, they add. Simple, right? These are also parallel, but opposite. So let's think of a tug of war. One side pulls one way, one side pulls the other way. One is using 1,000 newtons west. Again, I just put it on the west side, and of course they should be even. And the other side pulls with 1,500 newtons east. Well, who's going to win? The east side. Now, again, drawing them tip to tail, doesn't matter the order. If I draw them tip to tail, I go 1,000 west, and I start the next one, I just go back 1,500. Well, here's where I started, here's where I stopped. I usually use a dot where I started and an X. So if I change my color, my resultant, and again, this is not to scale, they cancel. So west is negative, east is positive. Mathematically, I'm going to take a negative 1,000 plus 1,500, and that's going to equal 500 newtons east. And that's represented by that smaller arrow. This is a not to scale tip to tail drawing. I kind of free-handed it, not a big deal. But when we add tip to tail, notice the resultant is exactly opposite. It touches the tail of the first one, and the tip is at the very end. Very important. They are not allowed to be added tail to tail. Okay, so what happens when they're right angles? We're going to make a right triangle. So I have a boat heading across the river at a velocity of 30 meters per second each. So you can think of it like I have a river and there's a boat trying to go across pretty fast. And the current is going south, so there's the water. So what's going to happen? Assuming the driver doesn't compensate. Well, if the guy wants to go across, he's going to have to aim up the river. But we're just going to say he shoots straight east. And what's going to happen? He's going to end up probably down the river, living in a van or something like that. So I'm going to make a little sketch. I'm going to represent each of these vectors with an arrow. I'm going to point them in the correct directions. So I'm going to start by going east. Why? Because we like to go east or west first, so we have normal sounding angles. That's 30, so I'm going to go kind of long. So my boat's going 30. Notice I'm going to leave the units off my picture. Then the water's going south at 10. This is where I started. This is where I stopped. Resultants are drawn start to stop. And I'm just choosing color to see it. Again, this is not to scale. This is tip to tail. This resultant is not. The resultant goes from start to stop. Well, what did I make? Oh, my favorite, right triangle. How do I get this angle? Well, let me go back and see. What direction is that? It's to the east and down. If I go back to my picture, if I go to the east and down, I have a southeast angle. That's how I check it. All right, so how do I do for a right triangle? Well, I'm going to find the hypotenuse. Throw this in here. 30, oops, I guess if it turns 30 squared plus 10 squared equals, okay, 1,000. The square root of 1,000 is going to be 31.62. Okay, so 31.62. That is the magnitude, how big the resultant is. Now I need the angle. I want to know this angle. I know it's southeast because I checked my chart. I'm going to stick, because these were given, to tangent, because this is opposite and this is adjacent. All right, so tan minus 1. Remember, when you're looking for the angle, you're using that minus 1. 10 over 30. All right, let's get this going, clear. Second tan, that's how I get my minus 1. 10 divided by 30 is 18.43. All right, writing out the vector answer. This is not, you just don't leave it like this. Your final resultant, just like these up here, I had an amount, that's a magnitude, and a direction. It is 31.62 newtons. Excuse me, we're on a different problem. Meters per second. You have to give the unit from the problem. At 18.43 degrees and southeast. There. All right. This problem is for you. I'm going to give you a moment, and you're going to do it in your notes, and we're going to check it. And the airplane is traveling north at a velocity of 150 kilometers per hour, and it encounters a wind from the east. What is the resultant velocity? Remember, a wind from the east is pushing which way? Think about that, okay? The wind is not going to the east. Wind is from the east. Winds are made and named based on that. All right, so you need to do this problem so we can check it when we're done. All right, thanks guys.